Okay guys, sorry I forgot actually to record my lesson today, so I'm going to do a quick video of what it was that you missed in class while you were out. This example comes from page 19, I believe, of your unit packet, so you can find that problem there. Sorry, my daughter's really excited right now. But anyway, you can find this problem and work it with me real quick to add on a new piece of information. So why don't you go ahead and push pause and see if you can identify the following things here, just based on what you remember. I'd like for you to attempt to determine the degree and the leading coefficient. Use that to write me a couple limits, sorry for that handwriting, for end behavior. And even further than that, go ahead and try to tell me the maximum number of roots or possible zeros, the maximum number of turning points, and I want you to go ahead and try to factor and solve for the roots here, which means you're going to set this equation equal to 0. Hit pause and come back when you think you have answers. Okay, welcome back. Degree here is 4. Leading coefficient is -2, which means I have an even degree negative polynomial, so both of my ends are going down to -infinity. Maximum roots are 4, turning points are 1 less at 3. When I go to solve this equation, I start by factoring out a -2x squared, and I'm left with x squared minus 3x minus 10. Do a little bit of factoring, x box maybe off to the side, and we end up with the factors of x minus 5, x plus 2. I set each equal to 0 now. Have an intense game of hide and seek going on upstairs. When I solve this one, I get an answer of 5. This one, I get an answer of -2. This guy seems to trip people up. I'm going to divide, and then I'm going to square root, and I get an answer of 0. So let me pinpoint those. 0, -2, 5. From here, I try to synthesize all of this information and talk about my graph. So I know I'm going to be going down on both ends, and I know I have roots at 0, at -2, and at +5, right around here. The trouble is, if you do this the way I instructed you to yesterday, you just start connecting the dots, and you run into some trouble, because if I connect the dots starting on the left-hand side, it would appear as though my function should be going up on the right. Some of you try and correct that by just curving down at the end, which also forms a problem because if I do that, I'm creating an additional root. So here's where the new info comes into play. I'm going to erase all of this. The actual graph for this function has the roots at -2, 0, and 5. But because of something called multiplicity, when I go up here, I'm actually going to bounce off the root at 0 and glide through the roots at -2 and 5. And this introduces the idea of multiplicity. So when I look at this factored function that I created, you'll notice this first factor has a power of 2 on it. The next one, it's kind of subtle, but there's a power of 1 on the outside. And the final one also has a power of 1. These powers on our factors are what we call multiplicity. And it's a very important characteristic of our graph. If we look at a factor and we identify that that factor has an even multiplicity, that means our graph is going to bounce off of that root. If, on the other hand, we have odd multiplicity, that means our graph will cross through the x-axis at that root. This is summarized somewhere in your packet. I think it's on, hold on a sec, the bottom of page 21 right here, this idea of repeated zeros, and we introduce that term multiplicity and talk about odd multiplicity and even multiplicity right here. So this is the mathematical way of explaining this, but I like to put it in teenager language right here. If the power on my factor is even, I'll bounce right there, and the associated factor here, remember, was 0, so I bounce at 0. If my multiplicity is odd, like it is on these ones, I'll cross through the axis at those roots. So we're going to clear this out right now and do one more example, and then y'all should be caught up to speed. So give me a sec. Okay, so I'm back with the next example. I think this is on page 23. Maybe it's a model problem following that definition that I just showed you in your packet, maybe page 22. You'll notice you've got several instructions here, and I'm going to start by really driving home the point about multiplicity that we just heard about. If I rewrite this function, what I'm noticing is that one of these factors, the multiplicity, is visible right here on the end. I see a power on top of my factor, so the multiplicity is 2. And these other guys, there's an implied multiplicity of 1. So I'm grounding this again in the idea that an even multiplicity value will bounce at that root and the odds will cross through. But to address part A here, apply the leading term test to determine end behavior, I want to look at this strategically and use the multiplicity to my advantage. So we're not used to finding the degree and leading coefficient in factored form like this. We're used to seeing something in standard form where I have all my terms listed out and I just find the highest power. I could simplify this by doing a whole lot of algebra simplification, boxes, distribution, things like that. Or what we talked about today is that the degree of a polynomial in factored form is actually the sum of our multiplicities. So that's 1 plus 1 plus 2, or a degree of 4. The leading coefficient here I can also find without doing all that multiplication by looking at the numbers in front of these x's, the 1, the 2, and the 1. So to find my leading coefficient, I will just multiply those together and I get 2. Moral of that story is that that's an even degree with a positive coefficient, so both my limits are heading toward infinity, going up on both sides. To do part B then, determine the zeros, this is actually nice because this function's already factored for me. So I have one root at x equals 0, another one when 2x plus 3 equals 0, and the final one when x minus 1 is 0. Right here I'll subtract 3 and then divide by 2, and it looks like my second root is at negative 3/2. Here I'll add 1, and it looks like my final root is at x equals 1. So good news, same skills as last time. The only difference is I need to state the multiplicity. So on this guy right here, I have a multiplicity of 2. That's 100% linked to that power. My multiplicity on the other two over here is 1, and that's related to the implied powers on top of those. So the only thing left to do is graph this guy. Just a sec. So I know I'm going to be going up on both ends, and I also know I have roots at 0, negative 1.5, and positive 1. Because positive 1 was a repeated root, that means when I go through at 1, I need to bounce right off the graph. Here I am with my completed sketch. Sorry about that one, it's kind of ugly. That's what you missed. Even multiplicity, we bounce. Odd multiplicity, we cross. See you guys tomorrow.